physicsninja.org.
Hi, today I want to look at a problem with RC circuits, and more specifically I want to consider the case where I have a resistor and a capacitor in parallel to each other. If you go in any undergraduate physics textbook, they always deal with a case where you have a resistor and a capacitor in series, but you never really see the case where they're parallel with one another. And I was asking myself why. So I went through all my textbooks. I went through General Physics by Sternum. Nothing there. I went through Halliday and Resnick and Walker. Couldn't find it in there. No discussion of the problem. I then went through the Young and Friedman book. This is the best book I've ever seen for undergraduate physics. Could not find the problem there. Then I went to a second year book, an engineering electromagnetics book. No discussion of the problem. So here it is. And what I like the most about this problem here, so I've drawn out the circuit on the left-hand side. I'm also going to include an additional resistor that's in series with my power supply, which is just a constant voltage source in this problem. So we're going to include that and see how we set up the equations. We're going to set up a loop rule and a junction rule, and we're going to solve the equations to get the currents in every single branch as a function of time. So let's see how we do that. Okay, so let's consider our circuit again. I've labeled the currents I1, I2, and I3, and I first want to examine what's going to happen basically at time equals to 0. I'm also going to start with the capacitor initially uncharged. So the initial charge on the capacitor is 0. If you remember your capacitor equation, that relates the charge on the plates to the voltage across the plates. This is basically going to mean that the voltage across the capacitor, at least at time equals to 0, is going to be 0. That's an important result right there. That also means that the voltage across any branch of a parallel circuit is also going to be 0. So the voltage across our resistor R2 must also be 0. And how we're going to obtain that? You can only obtain a voltage across a resistor equal to 0 if the current flowing through that branch is 0. So initially at time 0 we have no current flowing through the center branch. Now what we're going to do is, well, let's consider a loop and consider this blue loop here, and I'm going to add all the voltage sources, the gains and the drops as I go around this loop. So the first, if I start over here in the corner, the first thing I encounter is the EMF of the battery. As I cross the EMF, I get a voltage gain. The next thing I encounter is the top here is a resistor. As I cross a resistor in the same direction as the current, I'm going to get a voltage drop, and that voltage drop is given by Ohm's law, I1R1. And that's it. If I go down the center branch, I know I've just shown you that there is no voltage drop across R2. So therefore we're done. And then we go back to where we started. We must get 0 if we start, if we finish where we started. So therefore, just isolating for our current I1, we obtain that it's V over R1. Here's our initial current flowing through the battery and flowing through this top resistor. The current down the center branch is 0. That also means that the initial current for I3, if you consider now a junction rule, the junction rule tells us that whatever goes into the junction has to be the same current that leaves the junction. Since we've just shown that this term is 0, we also conclude that the current I3, at least initially at time equals to 0, is V over R1. So we know the current everywhere in the circuit at time equals to 0. Okay, so now let's consider the other limit. It's the limit after a long period of time. And I didn't say long. I haven't really defined what that means. But let's just consider very long until the capacitor is fully charged. So that means I'm going to get some positive charge on this plate. I'm going to get some negative charge on that plate. And there's going to be a voltage across this capacitor. So what does that mean in terms of the current flow in this circuit? Well, since I'm going to have a voltage across the capacitor, which is going to be given by the charge on the plates divided by the capacitance, you're basically not going to get any more current flowing for I3 in the outer branch. So what does that mean for the rest of the circuit? Well, again, I could choose to do a loop. And let's apply our loop rule. And let's do it over the same branch. Now I3 is going to be 0 now because there's no more reason now for the charge to flow in this section. I've got a voltage across the plates, and the electric field produced by the charges on the plates will cancel the electric field produced by the battery, at least in this section, the outer section. However, in the inner section, this inner loop here, current can still flow. So let's apply the loop rule to this section and see what happens. So again, if I start down here at the lower left-hand corner, the first thing I encounter is a battery, and I'm going from the negative to the positive. So I'm getting a voltage gain as I cross the battery. Next thing I encounter is my resistance R1. I'm going to get a voltage drop across that resistor, and that's given by Ohm's law. I'm crossing the resistor now in the same direction as the current, so I get a drop in voltage. Now I'm going to go through this middle branch, and as I go through the middle branch, I'm also going to get a voltage drop, and the voltage drop is going to be given by Ohm's law, and the voltage drop across the resistor R2 simply given by I2 times R2. Now I'm right over here at the bottom of this resistor. I go back to where I started. My loop rule tells me that the difference from where I start to where I finish should be 0. So that's it. Here's my equation now for the second half. Now, the other thing we know is we can apply junction rule. The junction rule still applies up here. Okay? At point A over here, I still have a junction. I have current flowing in, and I have current flowing out. So the general expression is simply the same one that I previously had. The current flowing in equals the current flowing out. However, we've just said that once this capacitor becomes fully charged, there's not going to be any more current flowing in that outer branch. So in this case here, I1, whatever's flowing into the junction is basically just going to flow through this R2 resistor. So if you simplify that now, I can substitute or get rid of I2 over here. And at the end, what I'm going to get is simply I1. I can factor that out. Now equals to 0. And final expression for the current, at least I1, which is also the current I2, simply the voltage divided by R1 plus R2. So there you have it. So we have our initial current, which was given by V over R. Actually, if you plot that as a function of time, this is what it looks like. So we've looked at the current, and let's look at the current I1 versus time. So initially I had a value that was pretty big. It was V over R1. And after a long period of time, I'm going to get a lower value. Okay, the value down over here is given by the expression I just obtained, which is the voltage divided by the sum of R1 plus R2. And as a function of time, this is what you're going to find. You're going to have an exponentially decaying function. I haven't proven that yet. I will in the next part. But this is what we're going to look for now. We want to see what is going to be the dependence of that current as a function of time. I've obtained the value now in the limit where time is very small and the limit where time is very long. Now let's look at some intermediate time values and see if we could obtain the current in the 3 branches. Okay, so let's go back to our problem. Now the goal here is to find the 3 currents as a function of time. So let's start with a couple loops. So I've plotted some, or I've drawn some letters here, A, B, C, D, E, and F to denote certain points on the circuit. So let's start with a loop rule that goes around the outer edge of the circuit. So we're going to start here. We're going to go all the way around and go back to where we started. Let's call that equation 1. So if you add all the potential differences, I get a potential gain as I cross the battery between A and B. I get a voltage drop now, I1, R1, as I cross the first resistor. And as I cross this capacitor, well, I'm going to get a voltage drop across the capacitor. I'll just call it V sub C. I can label it over here. And then I go to point E and I go all the way back to where I started. That has to be equal to 0. My second loop now, my second loop will be the inner loop. So the inner loop will be this one. The first two terms are exactly the same because I cross a battery and I cross the resistor, so those haven't changed. Now the next thing I do is I'm going to cross the resistor R2 in that middle branch, so I'm going to get a voltage drop. I'm crossing the resistor in the same direction as the current, I2, R2. And that's it. I go back to where I started. I have to be equal to 0. Remember, the goal is to find the 3 currents. That means you need at least 3 equations. You might think to do another loop over here on the edge. That's actually not going to help you. That's going to be kind of a combination of equations 1 and 2. The other equation that you need is basically just a junction rule, which is the one we've been using all along. So if you consider the junction rule either at point C or at point F, we're going to get equation 3, and that basically says whatever current flows into the junction has to be the current flowing out of the junction. So there you go. These are our 3 equations, and we have 3 unknowns kind of buried in here. We simply have to solve this equation, or this system of equations. The first thing that I can do is I can eliminate the voltage across this capacitor. Let's consider the voltage across this capacitor and use our equation. Well, the voltage across the capacitor is going to be the amount of charge on the capacitor. I'm going to call that Q3, and that's going to be related to the voltage across this capacitor. So let's eliminate VC and substitute for the charge as a function of time flowing through that branch divided by the capacitance. That's the first thing I could do. That means that my new equation 1, let's call it 1 prime, is simply going to be V minus I1R1 minus Q3. I'll drop the time label for now just because we're going to have to write that quite a bit. And that equals to 0. If I write equation 2 right underneath it, the one thing we're going to notice from both of these equations is that if you compare both of them, what you should see is that these last 2 terms from both equations have to be equal to each other, right? And that's true, right? The voltage across any branch in a parallel circuit has to be equal. So we have to have that I2R equals to Q3 over C. This is a very important relationship that we're going to be using later to simplify our equation. So we have kind of 2 important things that came out here from this analysis. Okay, so here we are now. My goal now is going to be to work with our equation 1 prime, and I want to eliminate I1. How do I eliminate I1? Well, I can use my junction rule. In junction rule, let's get rid of I2. I2, I can write it in terms of Q3 over C divided by the resistance, and this here should be resistance R2. So what you should get for I1 is simply Q3 divided by R2C plus I3. Okay, so now let me write equation 1 prime. It's V minus, I want to eliminate I1, so let's open up a bracket and let's tuck everything we have here from our junction rule into this equation. It's the charge flowing in this outer branch, R2C plus I3. All of that's being multiplied times the resistance R1 and minus Q3 divided by C equals to 0. What I like about this equation here, it's an equation and it's all in terms of either the current in this outer branch or the charge in that outer branch. So we can do a little bit of algebra now to simplify this equation. And if you kind of group some of the terms together, you should get an expression that looks like this. V over R1 minus I3 minus, there's a whole section here, which I'm just going to call R2C minus 1 over R1C multiplied times Q3 equals to 0. I'm sorry, that there should be plus if you did the algebra correctly here, because I factored out the negative sign here. Okay, we're going to multiply through now by R1C, and what's going to happen here, so I'm going to simplify this expression a little bit. We have to do a little bit of algebra. We should obtain an expression that looks like this, and you'll have to work this out on your own, but multiply times Q3 minus the capacitance times the voltage of the battery. Okay, now this term over here, there's a term over here which is a dimensionless term. I'm going to call this alpha. So let's label it here on the side. Alpha is simply this ratio of the resistances, R1 over R2 plus 1. So let's introduce that shorthand here, because this term appears in a lot of different places. And just to simplify the notation here, we're simply going to have alpha multiplied times Q3 minus CV. Okay, so now remember that I3, that's the current in the outer branch. That is by definition the rate of change of the charge Q3 over time. So if you just substitute that expression over here, we end up getting dQ3 over dt equals to alpha Q3 minus CV. Now this is a simple differential equation that we should be able to solve. Okay, to solve it, all we're going to do here is, let's start by factoring out an alpha. So this here becomes Q3 minus CV over alpha. This term here remains the same. And now we're just going to group some terms together. So let's group all the terms with Q3 on one side. So we have dQ3 divided by Q3 minus CV over alpha. Has to be equal to negative alpha divided by R1C multiplied times dt. Okay. So now all you have to do is integrate this expression on both sides. And you're going to integrate from zero charge on the plates to some final charge, Q3, on the plates. And you're going to integrate from 0 to time. Okay, and if you do that, well, all you're going to get here is the natural log of Q3 minus CV alpha divided by negative CV alpha. That has to be equal to simply minus alpha R1C multiplied times time. In order to simplify this a little bit further, all you have to do now is take the exponential on both sides and simply isolate. And what you're going to get at the end is simply an expression for Q3 as a function of time is simply going to be CV divided by alpha, 1 minus our exponential function, and the argument of the exponential is minus alpha multiplied times time, and R1C. And there you have it. And remember that our definition of alpha was just this dimensionless parameter, which was the ratio of the resistors plus 1. So there you have it, a complete expression for the charge in that outer branch as a function of time, or the charge on the plates as a function of time. Okay, so we've got our charge Q3 as a function of time. We've got our dimensionless parameter alpha that's defined here. We also have that the current I3 is simply the rate of change of the charge. So that one we can find right away, right? You simply take the derivative of that expression with respect to time. The first term's a constant. We don't have to worry about that. The second term now in negative alpha divided by R1C will pop out. And what you're going to be left with is simply that the current through this outer branch is V over R1, and the exponential term is going to be minus alpha T divided by R1C. All right. I2, the current I2 down the center branch, that's simply related to the charge Q3. So you can right away write an expression for I2C. I2C is simply going to be that identical expression over there. We're going to have V divided by, you notice the capacitances are going to cancel out here. So you're going to have V over alpha R2 and multiplied times 1 minus exponential of the same term, minus alpha T divided by R1C. And the last one is I1. It's the most complicated expression, but it's simply given by our junction rule. And we have both of these other currents. Therefore, you simply have to sum them up. So I1 versus time is simply going to be V divided by R1 plus R2. I've simplified some of the math here. You'll have to group some of the terms just to see how things are done, but it's very straightforward. Same exponential factor, R1C, plus V1 divided by R1, and the same exponential function that we've seen throughout this problem. So there you have it, folks. That's the three currents in the three different branches as a function of time. Now let's look at these expressions in a little bit more detail and see if the physics matches up with our expectations. Okay, so here are three expressions for the currents as a function of time. My expression alpha, which appears in the exponential functions. Now I've eliminated the alpha in the term multiplying these exponential functions just to have it in terms of the voltage and the resistances. But now what we can do is we can look now at these expressions let's look at the two limits that we first started with. So what happens at time equals to 0? What happens at a very long time? And now I can see what long time actually means. Long time simply means that the time is much bigger than this term over here, R1C divided by alpha. This is kind of the long time period. And this would be short time. So what do the voltages look like and the currents look like? So at time 0, what are we going to have? Well, I want to look at all three. So I1, I2, and I3. Well, some of them are a little bit simpler here. If you substitute 0 in here, you're going to get I3 is simply V divided by R1. What about I2? Well, again, that exponential function, if you substitute 0 in here, you're going to have 1 minus 1. That's going to be 0. So there's no current flowing through that center branch. And likewise, now if you simply add them up, you're going to obtain the same thing. That I1 is simply equal to I3. There you have it. That's the exact same result we had without doing a week's worth of algebra here. All right, what about in the long time limit? What are we going to obtain? In the long time limit, again, I want to look at I1 as a function of time, I2, and I3. Now in the long time limit, look what happens to I3. If you substitute a very big number here for time with respect to these other variables, that term basically goes to 0. You have an exponentially decaying function. Again, at time equals to a very long time, I2, the second term here vanishes, goes to 0, but you're still left with that first term. So that's V divided by R1 plus R2. And I1, on the other hand, again, you're going to simply obtain the same thing as I2. And this is what we previously had, just analyzing the simple circuit by taking appropriate limits. But you can see that our equations actually satisfy those two time limits. Okay, so let's graph things now to see what's going on. Let's start with I3. That was probably the easiest one. I3 started out at time equals to 0. Plot that one in blue. And at long times, I3 went to 0. And it had an exponentially decaying function that looks something like this. Here's I3. I2, on the other hand, I2 started at 0. I2 is in green. Started at 0, and it eventually went to this limit over here. So let's do, maybe I'm not drawing this 100% correctly, but just to give you the idea, it's just a sketch here. And I1, on the other hand, I1 started as I3. I1's in black, and I1 tended to this guy over here. So here's I1. Here's the current I3, and I2 is the green one over here. Oops. This here should say I1, as I said. There you go, folks. So there are the three currents for a RC circuit where we have a resistor and a capacitor in parallel to one another. And it's worth taking one more limit actually. What happens if R2 is very, very big? Imagine somebody just went up there and just cut the wire. Well, if somebody cut the wire, basically the resistance goes to infinity. Let's actually just get rid of it. There shouldn't be any current flowing through that section. So if R2 goes to infinity, this is what we get. Now, what do the expressions look like? Well, what happens to the current I1? Well, now we're basically left with just our simple RC circuit where we have a resistance in series with a capacitor. And that one's done in every single textbook. You see that if R2 becomes very, very large, the first term in this expression for I1 goes to 0 because I'm dividing through by a very big number. And I'm simply left with V over R1 and exponential. And what happens to the alpha term if R2 is very big? Well, this first term actually goes away and alpha simply equals to 1. So we're left with a much simpler time constant here. I2, on the other hand, has to be equal to 0. If the resistance is very, very big, there won't be any current flowing through there. And I3, on the other hand, has to be the same thing as I1. And we're left with our standard expression for the currents. And also, if you looked at the charge as a function of time on the plates, again, that expression for alpha would simply simplify to 1. And you'd be left with the charge on the plates simply looks like our standard textbook expression here. So our equations are consistent with all of the limits that we can look at here for this problem.